Here I summarize the things for you. You have U, you have H, and U is actually a better parameters that you can use when you're under a condition that's more relevant to your T and B. And H is actually more relevant to the P and T. du is equals to partial U partial T at constant V times dt. And then if you can recognize this is your CV, this is your CP, then you can write out this equation as well. From here, you should know that this is actually the internal pressure. And then you should actually know what's the definition of your mu J. This is excluded volume and then eventually lead to the mu JT. So based on the things you learned so far, that's pretty much all the equations you can actually get. We want to further expand this equation so that the equation can become more useful. So the things we do, okay, here is actually we want to further expand the second terms using some simple approximations. So here we know this term is called the internal pressure. So back to chapter 16, we say if you have P ideal, will be your P real plus your P internal pressure. In other words, you can actually write your P internal pressure as the difference between your P ideal minus your P real. So how can we actually do the P ideal? So for the ideal gas law, we know P is equals to RT over V. But of course, we won't just put these things in because it's not general enough. We can actually do, if I do the derivative of my pressure with respect to T, and if I multiply my T back, okay, I actually can get back to your ideal gas pressure. So we can actually eventually write your internal pressure term can be expressed as the ideal pressure, of course this is under constant V, okay, minus P. Okay, so you can actually write your second term in this form. So if you swap this term with this term, then that's how we actually get to this equation. So you can write your du equals to Cv dt plus T times this minus P dV. And this will be one of the most general equations for chapter 19. We're going to go through many applications of the first law of thermodynamics. You will see all the applications. You can always start from here. And based on the condition given inside the questions, you simplify this one and eventually lead you to the final equation that you want to use. Okay, so memorize it. Once you have this concept, for the H, it will be the same. We know this is excluded volume, right? Then you can also use these things to think about it because we say the V ideal is going to equal to the V real minus V excluded. Therefore, your V excluded will be V minus V ideal. And then we want to express our V ideal as T times partial V partial T at constant P. So you substitute your second terms, then give you the most general equations for your H. Okay, again, this is the most general equations for your H for chapter 19, so please memorize it. With these things, then you can actually use the van der Waals equation to show that these terms indeed give you the internal pressure. What you need to do is actually calculate T partial P partial T minus P. If you do this using the P equals to van der Waals equation, you should actually eventually lead to this. So do it yourself. For the excluded volume, here we need to actually make some simple approximation because here we only care about the excluded volume. Therefore, for the van der Waals equations, we actually throw out the internal pressure term. Therefore, we actually write the pressure like this. Once you have this, you can actually express your V as RT over P plus B. So you can show to yourself that V minus T times partial V partial T a constant P is going to equals to your excluded volume V. So I'm going to leave this 2 for you. Okay, I want to show you how you can apply this with 2 simple examples. So many times you will see this equation appear in your textbook. It says delta U is equals to CV delta T. But this equation can only be applied for very specific conditions. What's the conditions? You can actually write this. Delta U is going to equals to CV delta T. Every time you got these questions, always go back to the most general equations. Because you know your du is CV dt plus internal pressure times dV, right? So if you want to say this is true, that means what? That means the second term goes to 0. To make the second term goes to 0, what can you do? You can first do constant V so that the dV becomes 0, right? What other conditions you can actually make the second term become 0? Can you make these things become 0? What conditions you can actually make your internal pressure become 0? When you have ideal gas, right? So if you have ideal gas, then you know this will be true. Another thing is actually here we say the CV could be actually temperature dependent. If you want to just write CV delta T, then you need to know your CV cannot be temperature dependent. If CV is temperature dependent, then you know your delta U is going to equals to summation CV as function of T dt. So the reason we want to do this is simply to let you know you have so many equations like this in your textbook, and don't memorize those specific equations, because once you memorize the equation, you also need to know what's the conditions. If you just memorize this, and then if the question tells you right now you have an ideal gas and the CV is independent of temperature, then you can immediately go from there to here. So this is actually one thing you want to get used to it, okay? Always memorize the most general equations. All other things just a special condition of your general equation. And they will make your life a lot easier for this class.